All right, so 4.3, motion of charged particles in a magnetic field. All right, so we talked about the magnetic field. We talked about the magnetic flux through a Gaussian surface. We talked about poles and how magnetic monopoles don't exist. We talked about this magnetic force here, right, and how it's a cross product. So now let's return to that. So this cross product, the resulting force is orthogonal to both V and B, and it's given by that right-hand rule. So I want to point out that there are kind of multiple versions of the right-hand rule that you might see depending on where you look, and they're all the same. They are all the same. So there's one, which I kind of was describing before, where you have your 3, 4 here, and then you have, shoot, I'm no artist, but then you have your thumb here, and these fingers curl, right? So there's one vector here, so this would be like R for torque, and then this here, it would be like F, so you're going R cross F, and then your thumb points in the direction of the resulting cross product vector, which is torque in this example. Exact same thing. If we replace these vectors, it's the same thing as QV, so the direction of the current, right? Cross B, the direction of the magnetic field, and the resulting magnetic force that's felt. So that's one right-hand rule where you keep all your fingers together. There's just other ways of physically figuring this out that you might see in different textbooks or online, and so I'll clarify that because that often kind of confuses students. So another one is, I'm going to do my best to draw this, is you have your finger, your pointer finger, and then the rest of your, not that many humps, 1, 2, 3. The rest of your hand is like that. Is that the right? Yes. And then your thumb is indeed like that, but your middle finger here is poking that way, right? Let's see if I can maybe do that a little better. So this one is kind of doing that. So in this case, it's the same. You can see it's the same thing. You're just putting different fingers out to do different things. So in this case, you have QV again, and then this one here would be your B, and the resulting force vector here, this kind of like this would be B, and the resulting force vector would be given by your thumb. So in this one, there's no motion of your hand. You just hold your 3 digits, your pointer finger, your middle finger, and your thumb orthogonal to each other in this arrangement that I've tried to draw. And you point your pointer finger along the direction of current, or the movement of the charge, QV, and you put your middle finger in the direction of the magnetic field, and then your thumb points in the direction of force. There's also one that involves your whole arm. I'm not going to attempt to draw that, but just know that they're all the same. It's just the right-hand rule. One final thing is this is your right hand, right? That's important, and it's very easy to accidentally, and it's kind of silly, but it's easy to do, to accidentally pull up your left hand to figure something out, because often we're right-handed, and we don't want to put our pencil down while we're working on something, so we just stick out our left hand. But this is the right-hand rule because your right hand gives the correct answer. If this was your left hand, it would give an incorrect answer, and you can try it. Put your pointer finger in the direction of current as described on this page, and your middle finger in the direction into the page in the direction of the B field, the magnetic field. And if you were using your left hand, the force vector that results tells you that it would be down to the bottom of the page, which is incorrect. So your right hand gives the correct directions. The other thing that is important The other thing that's important with these right-hand rules is you're moving your hand to match the direction. You're physically pointing your finger in whatever direction in space you need to match the thing. You can also move your paper if you kind of get bound up and you can't twist your arm a certain way, or you can swivel in your chair, but this is a real physical dimension, important thing. So you can't just hold up your right hand arbitrarily into the air and get anything from that. You have to line your fingers up with the page in the correct directions, to the right, to the top of the page, into the page. You're moving your right hand in such a way, you're swiveling it with your wrist to line up these vectors. All right, so enough with that. So the motion of moving charges that are in a magnetic field and therefore experiencing the magnetic force that we just described, they're ultimately governed by Newton's laws, right? These charges have some mass, and we are figuring out what force they are subjected to or experiencing because of their whole charged situation. But their motion, where they move or how they move, because of this force, it's governed by F equals ma, Newton's laws. But it's interesting to note that since the magnetic force is always perpendicular to the direction of travel, right? This being the direction of travel, the resulting force perpendicular to that. Because it's orthogonal or perpendicular to the direction that it was traveling as it traveled through this B field in some other direction, the magnetic force can never change the magnitude of the charge's velocity. The magnetic force is never going to speed up or slow down this particle. All it's going to do is change its direction. Of course, it can have other forces acting on it. It could be, have electric force acting on it. You can also have some magic Wizard of Oz hand just flicking the charge, right? It can be subjected to whatever, but the magnetic force alone doesn't ever speed up or slow down the particle. It only changes its direction. And consequently, a moving charge that's only being acted on by the magnetic force always travels at constant speed and along a circular path, right? So let's explore that. So in mechanics, in your course before this one, hopefully you were introduced to uniform circular motion. Basically just various convenient ways to describe the motion of something that is traveling around in a circle at constant speed, uniform circular motion. We got we understood that there is an acceleration vector, and I would usually call it A tan or A perpendicular because it's perpendicular to the radial. Not A tan, A rad is this one, because it's perpendicular to the tangential velocity, right, at any given moment. So at that moment, what direction it is traveling, and then what acceleration is it experiencing it radially inwards. And that's this A rad here, and that's the reason that it changes its direction at all. And so here we have a perfect test bed or example of something that causes uniform circular motion. You have a moving charge, right? So instead of just any particle with velocity v, now we have some charge, and it's experiencing some velocity qv, right? And we're just going to say that it already had some velocity. It's not being slowed down by we're not considering any gravity or drag force or any friction with anything whatsoever. It's just kind of in its own little vacuum space in our minds. And it's traveling with constant velocity, and it has some charge, QV, and there's some magnetic field that is being applied to it, right? And so the magnetic field in this case, in order to produce a acceleration or a force that is radially inward on this circle, I'm going to put my index finger in the direction of the velocity. Well, I'll do one that's a little bit more convenient. We'll analyze it over here. So let's see. Here, same deal. This is QV, right? And what we want is for there to be some acceleration radially inward, a rad, right? And a rad is equal to, m times a rad is equal to F, whatever the force. And our force, we're saying, is only the magnetic force. So QV cross B, right? Hopefully I didn't lose you. This force is the magnetic force. And that force is the only force acting on this charge, Q, right? This charge Q here that is going around in a circle. And this charge Q has some mass. This charge Q has a mass m. It's tiny, but it has some mass. And so this magnetic force that is acting on this charge with mass m produces, according to Newton's second law, F equals ma, produces an acceleration, a rad, and it is radially inward if we orient our magnetic field the appropriate way. So I'm going to take my pointer finger and I'm going to point it upwards in the direction of QV, and we want our resulting force vector to be radially inward, right? So that there's a constant force acting radially inward on this particle. And so at this moment here, right, I'm going to put my thumb, which is what the force is given by. I'm going to put my thumb in the direction radially inward. And so this is my thumb, right? And so now, what direction does the magnetic field given by my middle finger, which is already being held out in a preformed formation in my hand, right? This one here that's on the page. Which direction is my middle finger pointing, thus designating which direction the magnetic field must be pointing to produce this situation? And it is inward, and so I don't know how to draw this, but it's pointing up at me, and this is my fingernail, right? It's pointing up at us, out of the page. So green, magnetic field is out of the page, B. And so basically, if we had this charged particle, QV, and it was traveling towards the top of the page at this moment, and we clicked on a magnetic field, and it's traveling at constant velocity, right? No other acceleration or force is acting on it. It was already traveling at velocity v up towards the top of the page when it's in this position, and at that moment, we clicked on a magnetic field in this whole area, B, which is out of the page, right? So just everywhere. There's a magnetic field in this whole space, up out of the page, everywhere. The sizes of my circles don't mean anything. I'm just drawing fast, and that is not an arrow. It's just a circle. Right? So the magnetic field everywhere in this whole space suddenly clicks on to be pointing straight up out of the page. Well then, this charge at that moment immediately is acted on by the magnetic force, which is this guy, right? And it's acted on in a given direction according to the magnitude of charge, right, which maybe I should do as red. It's acted on according to its magnitude of velocity, how fast it was traveling. If it was traveling faster, it would experience a stronger force. If its charge was greater, it would experience a stronger force. How do I know that? Well, all of this is in the numerator, right? And so it scales, it scales directly with the resulting force. And the magnitude of the B field contributes. So the larger the B field, the larger the force. And so you get this resulting force, which is what provides our radially inward acceleration. So, and to complete the picture, I guess, what would cause a B field to be pointing out of the page? Well, if we had, I'm going to attempt this, if we had some ginormous, north end of a magnet way behind this circular thing, and we had some ginormous south end of a magnet above it, like between you and the circular motion that is in the page, the south, right? Then the magnetic field would be traveling from north to south and acting straight up out of the page in that area. I know I drew it askew, but it's kind of hard to draw something stacked on top of each other and show depth and all that. But it's caused by north to south. So in other words, we can say, if you turned it sideways, this is the north end of a magnet, and this is the south end of a magnet. And our circle, right, it's going to be like this, but we're looking at it directly side on, so we only just see a line, right? And so our magnetic field goes from north to south and is coming straight through this loop, right? Straight through this loop. All right. And yes, there is net flux here, but it's not net flux through a closed surface that encloses this whole thing, right? We're not talking about a Gaussian surface that encloses this whole thing. It's just net flux through a thing. So this net flux equals 0 deal, this was, for an enclosing surface. So net flux through a surface that encloses a whole magnetic material situation is 0. But the surface is not a Gaussian one, it's just our little loop. Okay, hopefully I'm not confusing you. All right, so this is the situation. I've done my best to draw it visually so that we all know what we're talking about, right? So now let's throw some math at it. So uniform circular motion. We know that our A rad is equal to V squared over R, right? This is from previous course. And so if we have this situation here where we have the force equal to QV cross B, and saying that this is exactly 90 degrees, you can then say that this is QVB, right? So sine of the angle between them, and that angle is 90 degrees. Sine of 90 is 1, and so then you just get this full product of QVB. It's not diminished in any way because of the angle. It's full blast. Then we can say that the force, so this is A rad, right, the pink one up there, and so the force that this charged particle is experiencing is equal to, on the one side, m A rad, and on the other side, q v cross b, which is equal to q v b, right? It's just the same force, right? So this is what's causing the force, and this is what it causes the particle to do because of Newton's second law. So we can equate those two. And so since now we have an expression for A rad, I'm going to plug it in. So we have on the left side m v squared over r, right, ma, being equal to, and I'm going to skip all of this junk in the middle and go right to qvb. And I'm going to do this. All right, so now we can just solve for this r to find the radius of the circular path, because that's what r is the radius of this circle, r. And so if we solve for r, we get mv squared over qvb. B, and this is not squared. There we go. MV over QB. All right, so that is sometimes useful. There's some problems that deal with that. And likewise, we also have this concept of angular speed, which was omega, right? Omega. And there is some angular speed of the particle. Hopefully you talked about rotational dynamics or rotational things in your mechanics course. I hate doing too much review, but it's worse if you don't know what I'm talking about and you get lost. So if you already know everything about this, maybe you can just skip ahead in the video and find where you need to pick up. So rotation things, instead of saying something goes from x1 to x2, we say that it goes from theta 1 to theta 2. And instead of, in the linear world, this is linear, and this is rotational. In the linear world, instead of saying that something has a velocity x per time, delta x per delta time, which is equal to velocity, we say that it goes from delta theta to in some time interval delta t. So theta 1 to theta 2. And so we give that, instead of a v for velocity, we give it an omega for angular velocity, right? And the same deal extends to acceleration, but that's all we need. So angular velocity is omega, and omega is a very relevant quantity when you're talking about something that's traveling around in a circle. So we can talk about the rate at which this particle travels through some angle of this thing, right? So it's going from here to here. So theta 1 to theta 2, right, at some rate omega. So that's what we're talking about. So omega, we know from uniform circular motion in mechanics, is equal to v over r, which is, in this case, v q b over mv, or in other words, qb over m. So omega is equal to qb over m. You'll need that for some other problems. And it turns out that the number of revolutions per time, which we denote by this frequency f, that's omega over 2 pi. That's the number of revolutions per time frequency. It's referred to as the cyclotron frequency in this case, if you have magnetic force causing uniform circular motion, and you're talking about this frequency, right? There's some frequency, omega, which is angle per time, so radians per second. And that is the units of frequency, yeah? So this has units of radians per second, and yeah. And so that is known as the cyclotron frequency, because a cyclotron is an accelerator, like a linear accelerator you've probably heard of, right? Particle accelerators, all that advanced physics stuff. A cyclotron is a specific type of accelerator that accelerates particles in a circle using the magnetic force, exactly as we've been talking about here. So that would be the cyclotron frequency. All right.